Buenas tardes, bienvenidos a esta nueva versión del seminario de investigación del Centro de Modelización Matemática Mademat. Esta es de hecho la última charla de esta temporada. Nos ha ido bien y qué mejor forma de cerrarlo que con Marta de Elia. I think I switched to English. You all know Marta. She's one of best friends of Modemat and of ours, of course. And she agreed to share with us this research. And I'm really happy that this is the final session for this first season. It's wonderful to have Marta for this last session. So Marta, the public is yours. Welcome.
Thank you, Sergio. Thanks for the invitation. Of course, it's a very big pleasure for me to present at Modemat, and it will be even a bigger pleasure to be there in person. But I guess we should wait a little longer for that. In this talk, I'm gonna share some recent progress on the identification of non-local models using optimization and machine learning algorithms. The research that you're going to see is funded by the LDRD program, which is a lab-funded program, and by FILMS, which is a DOE-funded project. And FILMS stands for Physics-Informed Learning Machines. I didn't report here the list of my collaborators. It's long. I'm trying to give an overview of what we've been doing, but you see their names throughout the presentation. This is the very brief outline. I'm not sure I will have time to go through all of them, but I wanted to put some pointers. So in case somebody's interested, I'm happy to have follow-up conversations. I know that some of you are familiar with non-local models, but maybe not everybody is. So I will give an introduction to non-local models, a very brief introduction. And then after I convince you that these are good models, I will talk about how to pick the best non-local model given a particular physical system. Before talking about identification methods for non-local models, I will give an overview of the unified non-local calculus, which is a tool that we're going to use in the identification of non-local operators. And then I will present 3 techniques, hopefully 3, but probably 2 for kernel identification in non-local modeling. So I guess the most important feature of a non-local model is that the state of a system at a point depends on the state in a neighborhood of points. And what you can see from this figure up here is a space non-locality. So every point in a bounded domain depends on a neighborhood of points. We call this neighborhood non-local neighborhood, and delta is usually the interaction radius or the horizon. So the most important feature here is that interactions can occur at distance and without contact. And solutions of these models can be very irregular. They don't have to be differentiable. They can be singular. They can be discontinuous. The reason why we use non-local models as opposed to PDEs is because these models, in some circumstances, can capture effects that PDEs fail to capture. In particular, they can capture multiscale behavior. So non-local models can be seen as homogenized models. They can capture discontinuities such as cracks and fractures. And I think the best example in this case is the peridynamic model for continuum mechanics, which was introduced by Stuart Sealing at Sandia now 20 years ago. So it's been around for a while now. But they can also describe anomalous behavior such as superdiffusion or sub-diffusion. And this happens, for example, very often in the subsurface with when we want to describe pollutant transport, for example. The diffusion may happen faster or slower due to heterogeneities, for example. This is the simplest form of a non-local operator. It is an integral operator acting on this ball, on this non-local neighborhood. As you can see, there are no derivatives involved, so the solution can be nasty. And these operators are characterized by this function k. We refer to it as kernel. And k is application dependent and determines the regularity properties of the solution. The equations that we're interested in, at least for the purposes of this presentation, are non-local counterparts of wave equations, for example, as the one that I reported here. This is a second derivative in time. We consider more complex models, but to describe the methods, I'm going to use this simple example. There are many challenges, modeling challenges, numerical challenges related to the solution of non-local equations. And maybe the most obvious is the prescription of non-local boundary conditions. So the fact that every point interacts with the neighborhood means that when we get to the boundary, when we want to solve a non-local problem in a bounded domain and we get to the boundary, this property holds true. And so we need information outside of the domain to have a unique solution. And so we need volume constraints or non-local boundary conditions in the layer of thickness delta surrounding the domain to have a well-posed problem. In the case of fractional operators, where delta is infinite, we're going to need a volume constraint everywhere outside omega. Now, while mathematically this is perfectly fine, when we want to solve problems practically, this is not practical at all, because usually we're given surface data and not volumetric data. So even the simplest thing with PDEs, which is prescription of boundary conditions, becomes a challenge when we look at non-local problems. Anyway, today I'm not going to address this challenge, this specific challenge, but I'm going to address the challenge of finding the right kernel function. The kernel function cannot be measured. As I said, it's application dependent and it's usually unknown. So the question is, given a physical system or given some data, some measurements, how can we find the best K? So these are the most important questions that I will try to answer. I presented this very simple formula for a non-local operator, but one may ask, is this formula general enough? Can we use this formula to describe a large class of non-local operators, or are the popular and well-known fractional operators part of this class of operators described by this formula? Once we decide that this is the formula we want to go with, the next question, as I just said, is what is the best K? Given a physical system, how can we pick K? Now, in the models that we use, this is usually chosen heuristically. It's chosen a posteriori or depends on lab testing. So the next question is, can we design a tool, a data-driven tool, to identify the best kernel? So the answer to the first question is actually going to help answering the second question. And this is the very first part of my talk, which is the development, the design of this, what we call unified non-local calculus, where we introduce a sort of universal form of Laplacian, non-local Laplacian that includes a broad spectrum of non-local operators. And what we believe is that this unified calculus was one of the missing building blocks for the design of robust and mathematically rigorous and physically consistent learning tools or identification tools for non-local models. So in the next slide, I'm gonna try to summarize briefly this work on the unified non-local calculus. So the reason why we're after a unified calculus is because there are so many definitions of non-local operators in the literature, and sometimes this is overwhelming, sometimes it's confusing. I'm reporting here three classes. The first one is the one that I introduced at the very beginning, what can be defined as the standard non-local Laplacian. In the literature, there are also weighted non-local operators where the kernel function is a little bit more involved. So there are weights in the kernel function. And then we have fractional operators and with their definitions. There are several definitions of fractional operators. Some of them are equivalent, even though the equivalence maybe is not that explicit. If we look at these two formulas, it looks like at first they don't have anything in common, but they're actually exactly the same object. But there are other definitions of fractional operators that are not equivalent to this one, for example. So what we have is that for this first class of operators, there is I would say, a very well-established non-local calculus. This operator can be expressed as the composition of a non-local divergence and a non-local gradient. And there is a whole variational theory, what was introduced as the non-local vector calculus for this type of operators. For the weighted operators, the calculus is less established in the sense that there are some results, but they're not as complete and as established as the ones for the first class of operators. However, there are some results in the context of paradynamics. So for truncated operators where the kernels are paradynamic kernels, for example, there is quite some theory. For the fractional operators, which are probably as old as their integer counterpart, there is a well-established calculus. The reason why I put a star here is because, as I said earlier, there are different types of fractional calculus theories in the literature, and there are still actually some missing pieces. So here is what we did in this work. We proved that for every delta, so for every horizon or interaction radius, one can define an equivalence kernel. So one, given a weighted operator, one can find a specific K for which these two operators are equivalent. And that's why I claimed at the beginning that this is a very general, it's a simple but very general form of non-local operator that includes many other classes of non-local operators. So for every delta, we can establish this relationship, but what one can prove is that for a specific choice of kernels, the fractional operators are equivalent to these other operators that we have here. And in particular, when the non-local neighborhood goes to infinity, when delta goes to infinity, we can show that there is a convergence pointwise and in norm of Laplacian gradient and divergence to the fractional Laplacian gradient and divergence. This is good because this means that many results of this very well-established theory can be extended to this broader class of non-local operators. And in our opinion, this is also good because it establishes a connection, a bridge between the non-local and fractional communities, which started to talk to each other, but are not really fully talking to each other, and probably they cannot benefit from each other results. And in fact, in our when we started to work on this project, we found out that there are some results that are independently derived by non-local and fractional researchers, but are absolutely equivalent. Anyway, what I claimed earlier is that this theory can be used to, in addition to machine learning tools or optimization tools, to identify in a rigorous way non-local models. And in particular, by using this framework, this theoretical framework, we can guarantee that what we learn is well posed and it's robust and it's physically consistent. And at the same time, we can also enable the analysis and the use of the analysis of phenomena that are intrinsically non-local just by observation, but that weren't studied because of the lack of theory or the lack of simulation tools. So this is, I call it our recipe. So it's well established now that by combining machine learning and physical principles, we can get much better predictions than by just using machine learning as a black box. What we're going to add to this by surrogates here, I just mean any surrogate, polynomial approximation, neural networks, your favorite surrogate. But the addition for us is the unified calculus. So we're going to augment these methods with the theory that we developed, just so that we can provide non-local models, we can identify non-local models that are well posed by construction. Our working assumption will be that we have some high fidelity data, or that we can generate high fidelity simulations. So we have a physical system described by this high fidelity model, which is here. And what we claim is that we can use a non-local model to describe this high fidelity system. What happens usually is that the high fidelity model has to be solved on a very fine grid, so it's very expensive, while the non-local model can be solved on a coarser grid. Now, this high fidelity model doesn't have to be a non-local model. Actually, in most of the cases that we consider, this is a PDE. So to give you an example, think of subsurface transport. Subsurface transport can be described by a PDE that can catch the heterogeneities of the subsurface when the grid is fine enough, or when the grid catches the smaller scales. But this becomes not only very expensive computationally, but it also requires many, many parameters to be fully to be accurate. With a non-local model, what we're claiming is that the information is going to be all in this kernel K. So once we determine this kernel K, the kernel will embed the constitutive behavior of the physical system. And due to the non-locality, we'll be able to solve this system on a much coarser grid. Now, we developed a few methods to learn the best kernel K that describes a physical system. As I said, I don't know if I'll be able to go through these all methods that I'm listing here, but I'm just going to leave them as a pointer. And Sergio, stop me when I'm not tracking the time, and feel free to stop me when it's time to stop.
Oh, don't worry.
Okay. And as I go through the methods, also feel free to interrupt me and ask questions as we go. So I'm going to start from non-local operator regression. I will first introduce the method and then show some application to elasticity. So I like to describe methods just by giving simple steps. Once again, the goal here is to find the optimal kernel K. So the optimal non-local kernel. The assumption is that we have some measurements, some collection of measurements. So pairs of solution and forcing terms, which are high fidelity simulations, which come from high fidelity simulations, or can just be observations. We're going to approximate the kernel, and this is supposed to be a K. The surrogate that we're going to pick in this case is linear combination of Bernstein polynomials, which I'm reporting here. So the unknowns are the coefficients of this combination. And then we're going to minimize the residual. So we're going to minimize basically the non-local equation for every pair of solution and forcing term. The constraints are solvability constraints. And this is where the non-local theory becomes important. In this case, we're going to prescribe well-posedness constraints on the kernel. This is a little bit involved because we want to allow this kernel to be very descriptive. And while a very simple condition for well-posedness is that K is positive, this restricts the descriptive power of the kernel by a lot. And so we want to allow the kernel to be non-positive, to take on negative values. And this complicates the well-posedness theory. So this was the first work where the non-local kernel as in its functional form is learned. Previous methods identify parameters of the kernel given a functional form. Here we're learning the kernel itself. It's important also to note that the kernel, as I was pointing out, is allowed to be sign changing, and we learn a sign changing kernel without compromising the well-posedness of the final non-local model that we end up with. And as I will show in a couple of slides, This sets the groundwork for learning constitutive behavior for heterogeneous materials. And I'll show you what I mean by this in a couple of slides. I will start with the time-independent 1D, very simple example, just to show you our contribution. And then I would move to a time-dependent 2D case. So in this case, the high-fidelity model is this high-order PDE. It's a PDE that can be used to accommodate high-frequency response of materials. So by adding this fourth-order derivative, we can accommodate for high-frequency response of materials. And this has been used by some of our collaborators at Sandia. So this is what we're going to use on a fine grid to generate high-fidelity simulations. And what we're going to do is to learn based on this data. We're going to solve the optimization problem with our well-posedness constraints, and we're going to find the optimal kernel. So here I'm reporting the optimal kernel. What you're seeing here is the blue kernel, which is only positive. So just out of curiosity, we decided to learn a fully positive kernel. And the orange kernel is the one that is allowed to be negative. And as you can see, the differences are very, very tiny. But they're going to make the difference in terms of accuracy of the solution. So what we're doing now is to compare our kernel in action against high fidelity data. So the table is a little bit messy, but I'm going to summarize the information that you have here. So we're testing different horizons, so different deltas, and different parameters for the high fidelity data. The first column is the accuracy, so the relative error as it is defined here for a positive kernel, and this is for the sign changing kernel. So the second column is for the sign changing kernel. And as you can see, just by allowing the kernel to be slightly negative, we always get a more accurate solution. So this is sign that having a sign changing kernel is really important in this type of application. So anytime we're looking at mechanics and materials, as I will show you in the next example. So we're going to use exactly the same technique that I just described on a more complex problem. So what I'm going to consider here is our situations like this. So we have, for example, we have a bar, and the bar is heterogeneous. So the microstructure is periodic and is characterized by different materials. Here I'm considering materials with the same density, but different young moduli. And this is the same. This is a 1D setting. This is a 2D setting. And what we're doing is to consider different microstructures. So the high fidelity model in this case is going to be the classical elasticity equation by using the finite element method. So we're going to consider a very fine grid that can explicitly take into account this heterogeneities, and we're going to generate the high fidelity data. Some of this high fidelity data will be used as training. So we're going to use them as observation for our optimization problem. And another set of data is going to be used for validation. So after we have the optimal kernel, we're going to see how the kernel performs compared to this new set of data. So the non-local grid is going to be defined on what we call unit cells. So these tiny cells here. So the non-local grid is going to be much coarser. And there is a pre-step before doing the training, which is the coarse graining of the finite element solution. So basically what we're doing is to average the finite element solution that we get on every unit cell. The model is exactly the same. I'm reporting it just because, so in this case, we don't have a scalar, but we have a vector quantity. But as you can see, the structure of the operator is exactly the same. We have the second derivative in time, but the operator regression technique is exactly the same. So we're going to minimize the L2 norm of the non-local equation. Here in this work, we the main novelty of this work was the additional regularization term. And we call it energy constraint because basically what we're doing is to penalize the difference of the actual energy of the system and the computed energy of the system. And what I'm going to show in the next slide is that the addition of this constraint really makes the difference in terms of learning, especially when we test our optimal kernel on a new set of data that was not used for training. So we tested this method on both, as I said earlier, on both microstructures independently. So we don't use the optimal kernel obtained on this microstructure for this microstructure. So we did two separate experiments. So once the kernel, the optimal kernel is obtained, we test it on a new simulation using different forcing terms, for example. So the settings are completely different from the training settings, and we run the simulations for times that are much higher than the training time, just to test the generalization properties of our algorithm. Now, the graphs. So what you see here is the acceleration in the unit cell, in a specific unit cell. So this is, the first row is along X, the second row is along Y. And as you can see, along Y, since it's, the acceleration is much smaller, it's much more sensitive. So it's harder to catch. The first graph is acceleration without energy constraint, and the second one is with energy constraint. And as you can see, as I mentioned, the energy constraint really makes the difference when it comes to predictions. Now I'm gonna, oh yeah, I mentioned earlier, this is our current work. What I mentioned earlier was that this method is gonna be used to learn constitutive behavior. So one of the current lab funded projects includes starting from molecular dynamics data. So now our high fidelity simulations will be given by noisy molecular dynamics data. And starting from these, we're gonna learn the optimal corresponding non-local kernel. This is very important because it creates a bridge between scales. The non-local model, with the non-local model, we can run simulations at the continuum scale, so at a much, much larger scale than molecular dynamics. But we're going to use the data coming from molecular dynamics, which are going to give us information about materials. So the ultimate goal here will be to learn new materials, and the non-local model will help us in doing simulations at a much larger scale, which would take forever, either in the lab or by molecular dynamics simulations. The model is a little bit more complex. Here we have just preliminary tests where we reconstruct. So this is the kernel. It's given by a product of two functions. One depends on the bond, so on the distance between points. One depends on the bond strain, and our preliminary tests are very promising. So by using the same technique, we're reconstructing both components of the kernel. So now I'm gonna switch to a different technique. And the reason why, in this case, we switched to a different technique is mostly because the operator regression was not as performant on this specific case. And so here, I would say this is the no-local counterpart of PD constraint optimization. But the purpose is pretty much the same. So I'm gonna quickly summarize the setting. Which is very similar. We have, once again, high fidelity data. In this case, we want to simulate wave propagation. So it's gonna be a wave equation. The high fidelity model is a wave equation. So we want to simulate wave propagation through heterogeneous materials. And once again, we're picking a material where we have heterogeneities, but periodic heterogeneities at the microstructure. And the idea is the same. The non-local model at a much coarser scale will be able to catch the global behavior induced by heterogeneities at the microstructure. So we start from some high fidelity measurements. Once again, pairs of solution and forcing terms. Once again, we approximate the kernel by a linear combination of Bernstein polynomials. In this case, also in this case, the kernel is allowed to be negative. And this is very important, once again, to get accurate predictions. A positive kernel is not going to do the trick. Luckily, as soon as the problem is time dependent, conditions for the well-posedness are much less restrictive on the kernel. While for elliptic problems, they're, as it happens for PDEs, are more restrictive. Anyway, what we're doing here is to solve this optimization problem where we minimize the difference in a very standard way. This is a matching functional. We minimize the difference between the data and the non-local solution. And we have a standard Tikhonov regularization term on the coefficients of the kernel. The constraints are clearly the non-local equation for every pair, so for every K. And in addition, once again, we have constraints on the kernel. These constraints on the kernel are mostly added to guarantee that we can reproduce accurately the wave group velocity. And I'm going to explain what I mean by this in a second. One of these constraints, by the way, is basically equivalent to the energy constraint that we introduced for the previous problem. So that energy constraint, it's really important when it comes to this type of settings. So just a few words on the training data that we use. The high fidelity simulations are obtained with a solver that is exact for the velocity. And we're gonna use as training data this plane wave. So zero forcing term, zero initial displacement, and this is the type of velocity that we consider for different omegas. I don't know if this means much to you. It's just the optimal kernel that we find after the optimization. This is the dispersion curve. The reason why you want to look at this is just to make sure that this is positive because it ensures stability. Now, the group velocity. The group velocity is a very important quantity. At least we found out that it was a very important quantity for accurate predictions. So what happens here is we compute the group velocity, this blue line, the exact, let's call it exact group velocity. So based on high fidelity simulations. And then given our kernel, we compute the group velocity associated with our kernel. And we see that there is a very good match with high fidelity simulations. We compare this with some state-of-the-art kernel developed for this type of problems. This is a constant, it's the group velocity associated with a constant kernel introduced by Stuart Sealing for this type of problems. And as you can see, while this constant kernel, which was designed to catch the behavior at zero of the group velocity, this constant kernel behaves perfectly for low frequencies, but doesn't catch what's called the band gap. So at some point, the group velocity becomes zero. And this means that for values of omega that are bigger than this value around 4, waves don't travel anymore. While by using this kernel, waves will travel. And I'll show you an example of this. The second graph is just to show you how the group velocity changes as we change epsilon, which was the, sorry, as we change, yeah, epsilon and delta. So delta is again, the interaction radius. So the accuracy really is really sensitive. Our method is really sensitive to these parameters. And I have to admit, for now, we pick them heuristically. So these are hand-tuned for now. So validation tests. So we have our optimal kernel and we want to test it on settings that are completely different from the training setting because we want to see if our method generalizes well. So for sure, our kernel is going to do great on plane waves. What we want to see is if the kernel performs well on different types of problems. So we use a wave packet, which is defined in this way. And once again, we generate high fidelity simulations for different values of omega. And just to explain why we pick these values of omega, so this value, the first value is before the band gap or the band stop. So we pick 2. We pick a value that is very close to the band gap and a value that is beyond 4. So this is in correspondence of omega equal to 2. The optimal kernel performs very well compared to high fidelity simulations. When we get close to the band gap, the approximation is not super accurate, and this is because the match with the group velocity is not perfect. And then when we go beyond it, as you can see, the wave doesn't travel anymore in perfect agreement with the DNS simulation, with the high fidelity simulations. Just for comparison, we looked at the results obtained with the constant kernel, the state-of-the-art kernel, which performs well on low frequencies as expected, because it matches the behavior of the group velocity. It doesn't perform well at all when we get close to the band gap, but even worse, when we go beyond the band gap, the red wave, which is the one induced by the constant kernel, keeps traveling while the exact wave is not traveling. The last example for this technique is to model this type of situation. So we have a projectile that impacts, once again, a periodic order target as displayed earlier. And once again, we want to use our kernel learned on plane waves on this example. So on the top row, on the first column, we have the behavior of the optimal kernel for at low times, short times. And as you can see, our kernel performs pretty well in both cases, while the state-of-the-art kernel, which was actually developed exactly for this impact problem, still doesn't behave exceptionally for short times, but it does behave well at long times. So I don't know how I'm doing with time. I'm happy to stop here because I think it was 30 minutes, but
yeah, like you have like 5 more minutes actually.
Okay, so maybe I can quickly summarize this work. So for those of you who are familiar with pins, maybe this is, the first part is going to be a repetition, but so pins are physics-informed neural networks. And in this work, we introduce non-local physics-informed neural networks. And the idea is, I'm going to go straight to the graph. The idea is to, once again, learn the kernel, even though in this case, I'm learning just parameters of the kernel. So if you look at this non-local operator, what we're doing here is to learn the truncation, so delta, and to learn the exponent, so the profile of the decay. So it's still, the functional form is still given, but we're still learning a function here. And for those of you who are familiar with fractional operators, this is a type of, we can look at it as a truncated fractional operators of variable order. And what we're trying to learn here is the variable order and the truncation. So the idea of this method is to approximate both the solution and the decay profile with a neural network. And then we're going to minimize, once again, 2 components. One component is the equation residual, and I'm going to tell you what this equation represents in a second, and the difference between the measurements that we have, because once again, we assume to have high fidelity measurements, and the neural network, so our solution. These terms contribute to a loss function. So the sum of, we are going to minimize the sum of these terms, and what we're going to get are the hyperparameters of the neural network for S and the hyperparameters for the neural network for U. So what's this equation? I'm going to go back to the application. So this equation is the no-local shear stress equation for a turbulent flow, and it's the counterpart of the shear stress equation in the local case. The co-ed flow is basically summarized in this picture. You have a flow here between, it's wall-bounded turbulence. In this case, you have a moving plate, a fixed wall, and what we're going to look at is the velocity as a function of the distance from the wall. This operator D is similar to the operators that I presented before, but where this is not a second order, this is a first order operator that converges to, in the spirit of the unified non-local calculus, converges to a Caputo derivative for delta that goes to infinity, and then to a classical first order derivative for S that goes to 1. So we have DNS simulations. We have high fidelity simulations for this type of flow, and we're gonna use them in this setting. And what we surprisingly what we learned, this is the profile of S of Y. So this is the learned S of Y. We have several lines here. The dashed lines are the ones where we consider a very, very big delta, which basically means delta equal to infinity. So you can see this as a Caputo, a variable order Caputo derivative. And the solid lines are for truncated operators, so for a finite delta. But what's very interesting to observe is that the profile is pretty much the same for all these Reynolds numbers. And just to conclude, this is the computed stress. So we take our optimal parameters, our optimal profiles for every Reynolds number, we compute the stresses, and we compare them with the high fidelity simulations. And as you can see, they're basically on top of each other. I'm gonna conclude here. This is your last talk. I don't want to go too long, and it's almost happy hour time for you. So I'm gonna stop here. Thanks for listening, and I'm happy to answer any question.
Thanks a lot, Marta, for this very interesting talk. So I'm sure there's gonna be questions, so please.
Can I?
Yeah. Pedro, you can go.
Sorry, Marta, thank you for your presentation. I don't know if I missed, but you mentioned at the beginning that you approximate the kernel by Bernstein polynomial, right? Is there any specific motivation for that, or you can consider other type of polynomials? Or?
Yeah, you can absolutely consider your favorite approximation. We picked Bernstein. They have good approximation properties, but they're positive. They're once again they're nice functions, but you can do exactly the same thing. And we did try it actually with a neural network instead of Bernstein polynomials.
Have you tried radial basis functions, for instance? Or?
We didn't, but that's certainly a possible choice. That's certainly a possibility. We haven't. We tried the simple polynomials, for different types of problems, just combinations of 1x, x squared, things like this. That was not good. But again, we did try neural networks here. And the thing is, sometimes neural networks do make the difference because they're very descriptive, but sometimes they're not necessary, and they just increase the number of parameters that you have to identify, and so they're not worthy.
Okay, thank you. Other question is, how do you design the neural network? Do you have a specific profile for that, or?
So I'm trying to remember what activation function we used. It was a sigmoid. It's not a deep neural network. I think we used maybe 10 neurons per layer, maybe 10 and 10 layers and 10 neurons. I may not be super precise in this answer, but it's not bigger than that. It's a pretty small network.
Okay. Okay. Thank you.
Juan
But
Carlos?
it's sensitive. It could be sensitive to the hyperparam. I mean, to the width and depth of the neural network. But it didn't take too much hand tuning to find a good combination of width and depth. Sorry, I'm interrupted.
Thank you.
No, it's okay. Juan Carlos, you can go, please.
So thank you, Marta, for the talk. It's really interesting to see the local converting to non-local and changing the model in that fashion. And my questions, as you can imagine, concern the computational cost of that mainly, because as you know, in the imaging context, which is a two-dimensional steady state problem, let's say it is quite costly to get a solution, even if you have a parameter or solely a number. And I mean, if the training set is very large, then you get into trouble. Then if you get a lot of parameters as well, and you have to change iteration after iteration of the optimization routine, the whole kernel. So my first concern is actually if it compensates somehow to change the direct numerical simulation, which is, I know is you need a very small grid and you need a very precise solution. But if it compensates to do this non-local approach in the computational sense, because of the cost of the solution actually, and a part of that is a second issue: how sensitive is with respect to changes in the parameters that you may not control in the beginning. So, for instance, if you have a training set, I mean, you talk about I think the state and the forcing term. But for instance, if you change the boundary conditions, let's say, or things like that, how robust is with respect to that?
So, well, let me reply right away to the last one because it's a very short answer. It does work well if you change the conditions. If we change the loadings, we completely change the settings, and it does perform well even when you change those parameters. So it is robust with respect to data, such as boundary conditions and forcing. In terms of cost, as usual, you know, it's a matter of compromises, and it really depends on what's your goal. So first consideration, one of your questions was during optimization, you have to change the kernel and you have to solve for that kernel at every iteration. If you simply do, for example, what you have here, which is minimizing the residual, you only have to evaluate the operator. So it's a matrix, you don't have to invert it. It's true that it's non-local, so even just the assembly is very expensive. So there is that, but at least you don't have to solve at every step. In terms of, in general, computational cost, high fidelity versus non-local. In the case, for example, I'm just picking one of the examples that I presented. In the case of finite element simulations for the 2D plate, those were incredibly expensive because you have to resolve the microstructure, while the non-local model, the grid or the computational domain for the non-local model was much coarser. So as soon as you have your optimal kernel, if your purpose is, I want to find an optimal kernel and I want to use it in several settings, even different from the ones that I used for training, then it is really convenient. And this comment applies also, for example, to the molecular dynamic application that we're considering. Molecular dynamics simulations are incredibly expensive. So let's even say that you spend a lot finding the optimal kernel, then there are several settings that you can change. and still your optimal kernel is going to work. And you're going to save time because your grid is going to be coarser, and you can play with boundary conditions, you can play with loadings, and your kernel is still going to give you accurate predictions. So it is, I think it really depends on the application. It depends on how coarse you can be with respect to your high fidelity simulations. So I don't know, I guess my answer is it depends on your problem. You have to identify a problem where this is worth doing. So once again, if your goal is, once I have my model, I can test it on several different boundary conditions, several different loadings, then I think it's worthy.
Okay, thank you, Marta.
Sophie, ¿tenías una pregunta?
Hi, Marta.
Hi.
Yeah, well, you actually already answered my question, but I have another one. It's more about the concept, I think. How do you choose the interaction radius? Does it depend on the application? And I mean, is the smaller the better, or how do you choose the delta?
It's a $1 million question.
Okay.
No, I mean, so you can learn it. So in this context, delta can actually be part, and in the last application, can be part of your set of parameters that you want to optimize. So you can learn it. In general, delta, again, it depends on your application. So it tells you how far you want to go, right? How much information you need. In mechanics, it's very, very common to pick delta just as a multiple of your discretization step. Because what you care about is almost it's the behavior almost at the local limit, and the local limit happens when delta goes to 0. So what in mechanics people usually do is to consider delta equal to 2h or 3h usually, and that gives you answers that are good enough. It's clearly a modeling parameter, so you can do whatever you want with it. If your goal is to simulate, is to use a fractional operator, but because, okay, there's also the other question, because you asked me, is the smaller the better? Computationally, yes, because the larger delta, the more expensive is your computation.
Okay.
So in the case of fractional operators, delta is infinite. And so you may want to find an alternative or an approximation that has a smaller delta. But you already know from the beginning that the larger delta, the more accurate your operator is going to be. So once again, I guess, we could talk for hours about the choice of delta.
Okay.
For sure, adding delta as to your parameters to be optimized is an answer. We did that, and what you can find actually is that there's this phenomenon of operator mimicking. So the problem of finding the best kernel is imposed, is not you don't have a unique optimal kernel in general. And what we found, for example, when we were looking for the optimal kernel parameters and the optimal delta, there are several choices of parameters and delta that give you pretty much the same answer. And so if that's the case, so if different values of delta in combination with different values of the parameters give you the same answer, then you want to pick the smaller delta because it's the cheapest. Okay. So yeah, sorry, I gave you a 20-minute answer to a 1-minute question.
No, thank you so much.
¿Tenemos más preguntas? ¿Comentarios? Okay.
I have a quick one.
Dale, David. Dale.
Just a quick one. Yeah, thanks. Yeah, thanks, Marta, for the talk. It's really nice. I just have one small thing that I'm not sure about. How coarser can your non-local model be related to the high fidelity simulation.
Yeah. Okay. So I don't remember in the one with finite elements. I would have to check the paper, but I can do that afterwards. In the wave equation, it was 10 times coarser.
Okay.
I think, and that was for our optimal kernel. But for example, for the constant kernel, it was even much coarser than that. So that was our choice for the simulations. But in the constant kernel simulations, it was probably 10 times coarser. Sorry, 3 times even coarser than ours, or 5 times. Anyway, I would say you can go one order coarser for sure, at least in our problem. But I have to check the finite element because right now I don't remember.
I mean, it's application dependent in that case, is the coarseness that you have in your mesh.
Yeah, I wouldn't say there's a rule of thumb that you can apply to all these methods. Say, this is the factor between fine and coarse grid, for sure.
Okay, cool. Thank you very much.
Thank you.
Okay. Do you have more questions, más preguntas? Okay, if this is not the case, Marta, thank you again. As I said, this was the best way to finish this first season of our seminar. And of course, it would be great to have you here. Hopefully, this vaccine situation improves for all of us, because being young, healthy, and handsome is not a good combination during this time. Okay.
Yeah.
So,
can I say just one last thing? I don't know how many people are still on the line, but I wanted to advertise an initiative, which is this One Nonlocal World that we just started. We sent announcements today, and we're going to have an opening event on January 22nd. And registration is free. I cannot connect now. It's trying to connect. Okay. Registration is free. And we're going to have, it's a 2-day event, 22nd and 23rd. It's only in the, morning for me, maybe afternoon for you. It's a 5-hour a day. So if you're interested in Nonlocal, you want to know more about Nonlocal, I think this is a good opportunity. So I hope some of you will participate. I can send you, I actually sent the link to Juan Carlos earlier, so he has everything you need to know.
Okay. Cool, thank you. Thank you for the invitation. Ok, colegas, muchísimas gracias. Quiero agradecerles por su participación en esta iniciativa del seminario. Nos ha ido muy bien. Paramos por las fiestas. Happy Christmas. Hopefully a wonderful 2021. At least better than this 2020. Y nos vemos en enero. Continuaremos con las charlas en enero. Un gusto haberles visto a todos. Adiós. Cuídense. Bye, Marta.
Gracias. Felices fiestas.
Gracias.
Nos vemos. Happy holidays. Bye, bye.
Thank you, Marta. Bye.
Bye.